In this video, we'll have a quick introduction to what are called colligative properties. Colligative properties are a special set of characteristics that can be applied to solutions in which these properties don't depend on the identity of the substance that's involved, but rather depends on simply the quantity, the number of particles involved, regardless of what they are. And so, if we're to design this, these properties depend not on identity, but instead on quantity. This is going to be a little bit different than something like density. Density is a property that does very much depend on the identity of the substances involved. But with colligative properties, we're going to see that the identity of the substance doesn't matter. We're really looking at the quantity of things that are dissolved. And so we're going to introduce something called a Vanthof factor. Which is abbreviated with the letter I. As you can see, there is not a single I in Vanthof factor, but lo and behold, that will be our abbreviation for it. And I is simply the number of particles a substance produces in solution. And we're going to see that that really just means it's related to what type of electrolyte your substance is going to be. Breaks into when dissolved. And just like when we originally talked about electrolytes back in Gen Chem 1, we remember that soluble ionic compounds are always going to be strong electrolytes. That means they're going to break up into fully into their respective ions. So for something like CaCl2, calcium chloride, we're going to see that when dissolved, this breaks up into a calcium 2+ ion and 2 chloride ions. And since we have a coefficient of 1 and a coefficient of 2 put together, that equals 3, which will be our Vanthof factor for this substance. And so we're going to see that colligative properties, since they depend on how many particles are involved, something like calcium chloride becomes 3 particles in solution. Each unit of CaCl2 becomes 3 when it's dissolved. So it splits apart. And so we have to take account of that when we're going to be applying something like calcium chloride into colligative properties. We saw that something like, let's see, what would be a good example here? No, that's not going to work. No, aluminum sulfate is soluble. Yeah, we can do that. If we have something like aluminum sulfate, which presumably is soluble, right, because it's not one of the exceptions for sulfates, we're going to see that this breaks up into 2 aluminums and 3 sulfates, and put together, we're going to see that its Vanthof factor will be 5. Of course, you can also just add the subscripts of your ionic compound as long as you're aware of when the subscripts are necessary for charge balancing versus as part of a polyatomic ion. So notice here the subscripts of 2 and 3 for aluminum and sulfate, those correspond with the coefficients when it's broken up. And so you can calculate your Vanthof factor based on that. We'll talk about some more about this when we look at a couple of other types of electrolytes. Something that's a non-electrolyte, these are going to be covalent compounds, something like glucose. If we dissolve that, it stays as glucose, and so it has a Vanthof factor of 1. And we're going to see that all of our non-electrolytes are going to be covalent compounds. And any time we're dealing with a non-polar solvent, which is something we often do when we're studying colligative properties, that the value of I will be 1. Nothing is being broken off of a glucose molecule when it's dissolved. It simply gets surrounded by water molecules, happily engaging in their hydrogen bonding and dipole-dipole interactions, and there's nothing breaking off. Whereas with ionic compounds, the ions are separated by water, and so they will act as individual particles. However, with non-electrolytes, we're going to see that with covalent compounds, those are non-electrolytes, that we're going to always have a Vanthof factor of 1. So if we go back up here, this is for soluble ionic compounds, which will be strong electrolytes. And then we have the non-electrolytes, which are covalent compounds, or when water is not the solvent. So if you have a soluble ionic compound in water, you'll calculate its Vanthof factor by looking at the subscripts, or you can actually split it up and count the ions that are produced. If you are dissolving a non-electrolyte in water, or if you have a different solvent than water, your Vanthof factor will be 1. And unfortunately, it's a little bit more difficult than this. We haven't introduced weak acids into the equation. Weak acids have Vanthof factors that are slightly above 1, but not 2, very often very close to 1. And we're going to see that when concentration gets large, we start having weird things happening in the solution. So when the concentration goes up, the degree of separation of ions decreases. So we have an inverse relationship here. If we're increasing the concentration of our solution, we're going to see that it's very much harder to separate the ions. Even if they're fully dissolved, they may not be as separate. They may not behave separately. And so we may see that, if we have our calcium chloride, ideally, that breaks up fully into 1 calcium and 2 chlorides, which we can maybe represent here. Let's have the purple part be calcium, and we'll have the blue part be, no, let's use water as blue. How about orange for the chloride? Z, since there are 2 of them. If it's just 1 unit of CaCl2, yeah, we can break it up, and here's our water molecules happily surrounding those ions. Not a problem. I'm going to just put 6 waters. And so we see that things are okay. However, if we start adding more and more and more, as the thing gets more and more concentrated, whoops. I guess I'm only putting purple ones, that's okay. As we see that, oh, well, look, as we've put more and more and more here, we've got some kind of partial interactions happening between the ions again. And they're not necessarily strong enough to reform a lattice or anything, they're just interacting with each other. And if they interact with each other, they're no longer interacting with the water as much. And as a result, they kind of behave as though they've become 1 particle again, rather than being 2 separate particles, or in this case, 3 separate particles. And so as these small kind of pockets of interactions start happening as concentration increases, the more calcium ions we have floating in the solution, the more chloride ions we have floating in solution, more likely they are to interact with each other. Right? If we're just putting 1 little grain of calcium chloride into a liter of water, it's fine. It's a very low concentration. We are going to fully be able to say that, yes, it's going to break up into its ions. And so we might say that in reality, in a relatively concentrated solution. For calcium chloride, I is slightly less than 3. So it's not going to be exactly 3 because we start having the ions interacting while they're doing their ion dipole interactions with water. But it's not, I mean, they're still separate. It's definitely more than 1, so there is separation. It's still probably more than 2, but it's not going to be quite 3 in a relatively concentrated solution. In a dilute solution, dilute meaning the opposite of concentrated, in a dilute solution, for CaCl2, I is approximately 1. And so, approximately 3. Again, depending, since these terms concentrated and dilute are relative terms, they're not absolutes, I can't say, well, anything at below 0.05 molar would be dilute, right? It simply just depends on the individual solutions and the affinity of the ions for each other. And so we can just make these approximations. If your solution is concentrated, your I will be less than expected. If your solution is relatively dilute, your I will be approximately what you'd expect based on its chemical formula. And so with this, we're going to learn a couple of fun little tricks we can do with these colligative properties, understanding these Vanthof factors. And those will come forth in the next couple of videos.